All right, today we're going to take a look at sections 5.4 and 5.5. I feel like that they make the most sense merged together. It's really just a way to split some material up, and since we have a longer kind of class session with the Tuesday, Thursday, it works really well to put it into one section of material. What we're covering in sections 5.4 and 5.5 specifically is exactly what your antiderivative gateway on Thursday is about, okay? So take note of that. You have your second gateway, and it's happening on Thursday, just like the first one, but we're doing antiderivatives instead of derivatives. So the first time, you have an opportunity for extra credit if you get full credit on it the first time you take it. After that, it'll be posted and everything for you to start coming in and doing retakes on that quiz on either Friday or Monday. If I can get to it, it'll be on Friday that it'll open up for you to have that opportunity. If not, for sure by Monday, okay? So as we get started with this, I'm going to mention first what the fundamental theorem of calculus is. And so the fundamental theorem of calculus says that the derivative, that's that d dx notation, of the antiderivative, that's the script like looking s thing from a to b, or a to x, excuse me, of f of t dt is f of x. What this actually is saying to you is that the derivative of the integral, or the derivative of the antiderivative, is the function itself. So this is kind of like back in the day when email was kind of new-ish. I have a grandfather, he's in the nursing home right now, and he was pretty with the times. And he'd get these very cool things in his email that said something like, take the year and multiply it by this and add something, and then you do something with your age, and then you take these pieces out, and all of a sudden you're back where you started, and he's like, whoa, that was crazy. That's all this is. This is saying that if you multiply by something and you divide by something, you're back with the something you started with. If you add something and you subtract something, you're back at the something you started with. Therefore, if you take an antiderivative and then you take the derivative, you're back where you started to. That's all that says. Now, an antiderivative, let f be a function. We're going to use the capital F to identify something as the antiderivative of the lowercase f. So if we took the derivative of capital F, we'd be back with f as it was originally. That's the notation we're going to be using. Okay, so this isn't so much like a definition, it's more about the notation that we're going to be using and how we're going to be using it. So generally speaking, we will be using capital letters when we take antiderivatives, kind of like we used primes when we were taking derivatives. All right. Does everybody have those? Not quite. Sorry. Okay, did everybody catch up? Sorry, I tend to talk fast sometimes. All right, fabulous. What I want to remind you of is things that you already know to start with. These are some of the basic rules. It's partway down your page that you're looking at on page 1 anyway. Basic rules of derivatives. The derivative, or the constant itself, is y equals b. So what is the derivative of the constant y equals b? What is it? Yeah, it's 0, right? The derivative of a constant is 0. Let me change it to white. So this is saying that we're using primes, right? Y prime is 0. Okay? This is all just stuff you already know. Most of you got through all your derivative stuff just fine, so I know you know it. So the derivative of a constant is 0. What's the derivative of ax plus b? It's just a. Good. So the derivative is a. What's the derivative of the power rule? X to the n. This one's y'all's favorite. So nx to the n minus 1, right? Decrease the exponent by 1, multiply by the original exponent. Sometimes get tripped up, I know, on the exponential rule. What's the derivative of y equals b to the x? Do you remember? Yep. I usually write my b to the x first, but you're right, Paul. It's ln b and b to the x, just because I don't want you to think the b gets multiplied by the other b somehow or something. So b to the x ln b. E to the x is the best one ever. What's the derivative of e to the x? E to the x. Yep. And the last one, we didn't identify it as a specific rule, but we did it with the chain rule. When we had e to a power, the derivative of e to a power is e to a power, right? So that's e to the same ax. But then we have to do the derivative of the power. So what's the derivative of ax? A. So e to the ax times a. There's a few more, but let me make sure everybody's good with these first. So we've been doing a whole chapter with this stuff, right? Quizzes and tests and so forth. There were a few others that we had. We had a log rule, a constant multiplier rule, and a sum difference rule. So what was the derivative of natural log of x? 1 over x, right? What happened when we had a constant multiplier, a number in front of another function, and we took the derivative? It just goes with it, exactly. So it's just the same constant that's already there and the derivative of the function as though it weren't there. And then what happened with sums and differences? You're thinking of product rule, so slow down. This was not product, this was just the sum and difference. Right. Yeah, the derivatives of each one of them individually, which is what we wish were true for, all things, right? That would make things easier, but it's not. All right, so these were not all of them are basic rules, but almost all of them are. These are our basic rules for finding derivatives. Very familiar, we've done them a lot now for weeks. What we're going to do now is we're going to go in reverse. Instead of starting and finding a derivative, we're going to attempt to go backwards. So it's almost like we're starting on the right-hand side of this and we're going back to the left. All right, that's how it's going to feel. So everything that we do, we're going to undo that kind of an operation. So for example, if you have a constant, k, it's actually a lot like this one right here. A is a constant, just like k is a constant. And if I went backwards, what would I get? Well, I'd get x multiplied by that constant. Make sense? So if I'm taking a look at finding the antiderivative, first of all, it needs to be a capital Y, so make sure your y's look capital. We'll be dealing with f of x's and so forth more than y, but capital Y. And this would actually end up with kx, because the derivative of kx would be k. But did you notice over here, when this was ax, it said ax plus b? And the reason it isn't in the derivative is because the derivative of the b is 0, right? Just like the very first derivative on here, it's a constant. The derivative of b is 0. So every time I take an antiderivative, I'm going to put plus c on the end. C just stands for constant. What's that? Every time. Yeah. And the reason is because, again, if I went from this side backwards on the screen now, and I took the derivative, the plus c would become 0. Okay? So it's kind of like imagine a parabola, just the plain y equals x squared parabola. Okay? Everybody has a picture in their mind of that, yes? Okay. Now imagine if you took that graph and you just shifted it up 5 units or down 5 units. Would the slope change at all? No. It changes the location, it changes where it is, but it doesn't change the shape, right? That's what's happening here. Because derivatives find slope. So when I take a derivative, that plus whatever on the end, that vertical shift doesn't matter because it doesn't affect the slope. So it's possible when I take the antiderivative and I go backwards, I actually have some sort of a vertical shift happening that disappears if I were to take the derivative. Okay? So when you take your quiz on Thursday, sometimes I will have students write a big old plus C at the top of their page so that they don't forget to put plus C on every single one of their answers. I had a student, it's been many years ago, on the test, and he got them all right, but forgot plus C on every single one, which meant he got them all wrong, right? And that's what it meant, because he was missing the plus C. He came in, he retook it, he was fine, it's no big deal. But that's one of the sort of cautionary things. The second one is the power rule. So before, when we did the power rule, we took the exponent and we multiplied it down in front, right? And then we subtracted one from the exponent. That's what we did. Well, the opposite of subtracting from the exponent would be adding to the exponent. So here's that capital Y. We're going to take that exponent, and instead of subtracting one, we're going to add one. Instead of multiplying, we're going to divide. And instead of multiplying by the previous exponent, like we did with our other rule, we're going to multiply or divide by our new exponent. So it ends up being n plus 1 that we're dividing by. I need a plus C on the end, but I'd like to talk about this just a little bit more. Take a look. If you took this and you took its derivative, what would happen? Well, you'd take the n plus 1 and you'd bring it down to the front and you'd multiply by it, and it would therefore cancel with the denominator, wouldn't it? And then when you decrease to the exponent, you'd be right back to the n where you started. So you should be able to undo everything you're doing with antiderivatives and make sure that you end up with what you expected because you know how to do derivatives. So you can always undo your antiderivatives. These are so tiny and tight in here. I should really change the size and how much is on my screen. Okay, the next one. 1 over x. Whose derivative was 1 over x? Log x. So this is, and it's natural log, right, Mark? And there is one caveat to this. This feels a little bit funny, but you actually need it to say absolute value x. There's my plus C. Why? Well, the reason I need it to say absolute value of x is because the input for logs can't be negative, right? So I need to make sure when I'm creating this that I don't inadvertently create something that actually doesn't exist. And if I don't specify that I need to have an absolute value, then that's exactly what could happen. So I do need absolute values whenever I take the antiderivative of 1 over x. Y equals b to the x. That's the one Paula had helped me with. And we said that it was b to the x ln b, right? So the b to the x stayed the same, agreed? Yeah, so it will here as well. But before we multiplied by ln of b, so what do you suppose we're going to do now? Divide by ln b. So we're dividing by the natural log of b. Don't forget your plus c. And now you appreciate e to the x even more. If the derivative of e to the x is e to the x, what do you suppose the antiderivative of e to the x is? E to the x, yeah. Very good news. Like I said, I'm still writing too large. Oh my goodness. All right, so here's y, and it's e to the x. All right, y equals e to the ax. Wasn't exactly one of our simple rules, but we sort of threw it in there because it is considered a simple antiderivative rule. So when we did that on the previous page, we said that that would be the same e to the x and then multiplied by a, right? So this will again be the same e to the x, but what do you suppose we will have to do? Divide by a, exactly. Everything's happening in reverse. What's the? Thank you. See, I even forgot him. I'm zooming in and zooming out. That's the excuse I'm going to use. Yes, sir.
Leave the A in the exponent?
Oh, you do. I'm sorry. I got carried away. Thank you so much. There should be an A there still in the exponent. Yes. Okay, constant multipliers and sum difference rules work the same way, okay? So just like with our constant rule for taking derivatives, constant rule for taking derivatives means it just comes along. So if I want to take the antiderivative with a k that's involved, that k comes along and I just take the antiderivative of what's multiplied by the k. K, of course, is a number, just a constant. And if I want to take the antiderivative of two things that are added or subtracted, I just take the antiderivative of them individually and add or subtract the results. These both still have, I'll put plus c on the end. It's not necessarily necessary because I'd get the plus c out of the f of x or the g of x, but we'll put it there just for good measures. Which one? Those last two? All I'm doing is I'm taking an antiderivative of each of the pieces here, and the k just comes along for the ride, just like it did for derivatives. The antiderivative of f of x is capital F of x. The antiderivative of g of x is capital G of x, whatever those functions are. So they'll change depending on what kind of function I'm dealing with. Maybe it's a power rule, or maybe it's a log rule, or something like that. We'll go with what they are. But the numbers themselves, or the addition or subtraction, just occurs like we would kind of expect it to. Okay? So what we're going to do next is a bunch of examples. With the exception of the very last, well, the first several anyway is what I'm going to say. We'll go. They feel very much like what you'll see on your antiderivative quiz. So if you want some practice besides your homework, because you of course have practice in your homework for your antiderivative quiz itself, there's also a handout out on Canvas that you can print that's additional problems for antiderivatives, I believe. I'll double check that later to make sure it's true, but I believe so. So we're going to do some examples of these. We have a couple on this slide. We're finding the general antiderivative. And then we're going to check to make sure it works, at least mentally check. We don't necessarily have to write it down, but check to make sure that it works by taking the derivative and making sure we actually get what we expect it to get. So on the first one, that 7 in front is that constant multiplier one that Mark was asking about at the end. What's going on with the 7? Well, it just comes along for the ride. So I don't have to do anything with it except to drag it along. I really am dealing with the x squared, though. Okay? So what do I do with x squared? What will it become when I take its antiderivative? X cubed. What else? Divided by 3, right. X cubed divided by 3. So we increase the power by 1, that's the x cubed, and then we divide by the new power, the 3 on the bottom. Okay, the next part is a subtraction sign, but then it says e to the x. What is the antiderivative of e to the x? E to the x, absolutely. And then I need plus c. So let's mentally check to make sure that we get what we're expecting to get back at the beginning. If I were to take the derivative of 7x cubed over 3, the 7 would stay and the 3 would stay. What's the derivative of x cubed? 3x squared. And the 3 that you said first, Mark, would cancel with the 3 in the denominator, right? So we would, in fact, get back to 7x squared. What's the derivative of e to the x? E to the x, just like what we began with. And what's the derivative of a constant? 0. That's why that's happening there at the end.
What's the little line thing there?
Okay, so this is notation. It was on the first page. We didn't talk a whole lot about it, but it's notation. This notation, it's not a line. It looks like a script S. That made it almost look like something musical. It's a Greek letter is what it is. It's a sigma. So this is a Greek letter, and it means antiderivative or integral. Okay? So So it's telling you what to do by its notation. It's kind of like if a problem started out by saying f prime, you would know I'm taking the derivative, right? It's notation to tell you the same thing that the words would. That's what this is. It's notation saying antiderivative. Now, this piece at the beginning and this piece at the end, they go together. It's kind of like the beginning of a parenthesis and the end of a parenthesis. The beginning says take the antiderivative. The end says your variable's x. And I know we've talked about this before, but let me remind you, the reason that matters is because there's calculus done with multiple variables. I get that we're not doing it, but that's why that notation is there, is so that you can build upon it and you can eventually do it. Your textbook actually has multivariable calculus toward the back. If you were taking, if you were a business major at OU, you would have 2 semesters of calculus and you would get to multivariable calculus in this textbook. So it's multivariable calculus. That's why they put the dx on the end, is because they're reminding you, we can think of it that way, that your variable is x. Okay? So this is saying take the antiderivative for the variable x. So when you've done that, both pieces go away at the same time, just like parentheses would. So let's do this again for the next problem. Now I'd like to sort of draw out your attention to the fact that this right here can be rewritten like this instead. Agreed? It's true, yes. And it's more helpful to think of it that way. Because what that means is that the 1/3 at the beginning is just a constant multiplier, just like the 7 was at the beginning of the last problem. So it comes along for the ride. What is the antiderivative of 1 over x? What was it? ln of x. And it's absolute value. Okay? It's one of the antiderivative rules we just wrote down. The antiderivative of 1 over x is the natural log of the absolute value of x. And then what is the antiderivative of e to the 3x? E to the 3x over 3, right? Good. We'll get the plus c at the very end. I'll just do it at the very end. We still have one more piece. 2. What's the antiderivative of 2? (2x), exactly. So plus 2x, and then we'll put at the very end that plus c that we are going to always remember. The antiderivative of 2 is 2x, because the derivative of 2x is 2. Yeah. Okay, so let's start with the answer we just created and go back and make sure we actually get the problem if we take its derivative. If I take the derivative of the 1/3, the multiplication with the 1/3, the 1/3 stays. The derivative of natural log of x is 1 over x. So that part's okay. The derivative of e to the 3x over 3. Well, the over 3 part would stay. And the derivative of e to the 3x would be e to the 3x times 3, which would cancel with the 3 in the denominator. And then the derivative of 2x is 2, and the derivative of the c is 0. Okay, I know it's like we're going backwards. We are, and it takes a little bit to adjust your thinking. There's applications, we're just not there yet. It's like my second grader asking, or my first grader asking me, when am I going to use division? Because she doesn't know what division is, but I can't really tell her how it's going to be used until she learns how to do it. You know what I mean?
Use this stuff like
Hold
in the
tight.
business world?
Yes, you can. Yes, you can. We're going to see examples. It won't be this lesson for the business examples that are what you're thinking about, but we will have a section where we have some examples, yeah. All right, let's do another example. Got 9s everywhere. All right, what is the antiderivative of 9 to the x? Fabulous. 9 to the x divided by the natural log of 9. Okay, so somebody else help me out with the 1/9 x. What's the antiderivative of 1/9 x? I'll help you out. There's 1/9. Now what? What do we do for the x? Nope. It's not logs. Here's what you need to remember. This is x to the 1, right? This is the power rule. I need to increase my exponent by 1, which will make it x squared. And then to divide by that new exponent 2. X squared over 2. And the last one, I know we've talked about this, but it might be something you just don't deal with very often to think about too. The power 1/2 is the same thing as a square root. So it's another power rule problem, just like the one before. The 9 will stay. But I need to increase my exponent by 1. So what is 1/2 increased by 1? 3 halves. So I'm going to multiply this by x to the 3 halves. And then I would divide by 3 halves. Now that's really ugly, the dividing by the 3 halves. And it's really not all that pretty that it's written as 1/9 times x squared over 2. Now, on your quiz on Thursday, absolutely you would stop here. You'd move on to your next problem after you do the plus C, of course. But for the things that we're working with, the simple cleaning up of things, we expect that you would do that on a regular basis. So what would that maybe look like? Well, the 9 to the x over ln 9 would stay. This would be x squared over 18. And then right here, dividing by 3 halves is the same as multiplying by 2/3. Right? Division by a fraction, same as multiplying by the reciprocal. So if we simplify this, the 9 and the 3 would cancel to a 3, and I'd have 3 times 2, or 6. So this would be plus 6x to the 3 halves, plus my c. So that would be the cleaned up version of what we would get for this particular problem. So you'll clean things up like that on your homework, but then on the quiz, I'm interested in do you know the rules, so I don't need you to show the cleaning up part on that part of the test, the quiz, okay, the Thursday one. Okay, so we're going to start developing the whole how do I use this bit with the next problem. It's not going to hit exactly what you're asking me about, Mark, but we're sort of moving in that direction, okay? So, piece by piece. Find the general antiderivative. That's what we've been finding. For this function, c of x gives you an equation. It's dollars per unit squared, where x units are produced. Then label the units on the antiderivative. Okay, so it's wanting you to find the model with units. That's what you were working on in 5.2 that nobody asked me any questions about, so it must have seemed pretty straightforward, I hope, since you weren't asking me anything. So let's take a look with our new material here in this section, and then we'll combine it with section 5.1. So the small c now is a capital C. The 0.8 is a constant multiplier. So this right here is simply 0.8 times 1 over x. That's what it is. What's the antiderivative of 1 over x? Yes. And you actually kind of have a choice here. If you want to put the absolute values, you can. If you left them off, they'd be okay. Why? What is x? It says it in the problem, guys. What's x? Units produced. Can that be a negative number? No. The context here rules out the ability to have a negative number. So it would be perfectly acceptable, if you wish, to simply write this as natural log of x because the context won't allow it here. Okay, sometimes the context will, and so we need to be careful. But this one, it doesn't allow it for the context. So if you left it off for this, it would clean up the look of the equation, and it would make sense to do so. If you leave them on, it's okay too. I don't want you to think it's not, but I'm pretty sure if you looked at this one like in the back of the book, they won't be there. So I don't want you to be like, well, what'd they do with their absolute values? Probably that. Okay, a couple more pieces, or one more piece anyway, this one right here. All right, the number here at the beginning is a constant multiplier, so it simply joins us in the antiderivative, 0.38. What's the derivative of 0.01 to the x? Sorry, the antiderivative of 0.01 to the x. We did it with 9 to the x just a minute ago. What was the antiderivative of 9 to the x?
Yellow part follows on, right?
So this right here is what I'm talking about, right? The antiderivative of 9 to the x is 9 to the x over ln 9. Yep, the yellow part already falls down. I already wrote that. It's there. But what's the antiderivative of the 0.01 to the x?
0.01 to the x over natural log of 1/1.
Yep, like that. You can write it as though the whole thing is over it. You could write it like I did kind of originally where it's really just underneath the 0.01 to the x. It doesn't make any difference. It's all being multiplied, divided, so it's irrelevant. All right, I need one more thing equation-wise, and then I need some model unit stuff. What does my equation need? Plus c. All right, that vertical shift we were talking about going on. Units. Units are so cool because you almost get them for free when you're taking a derivative and then doing the derivative units, or you're taking an antiderivative and you're doing the antiderivative units. So what we see here is the units written right here, and they will be almost the same. What we have to consider differently is that when we took derivatives, we always said that the output was output per input. Nod your head if you remember that. Okay, so we always got this like per input component, right, when we took a derivative. Well, what we're going to be doing then is we're going to be taking the per input component off. Now this one's a little bit different because it says per unit squared, and my input's just units. So when I take a per unit off, I'm not going to take the per unit squared off, right? I'm just going to take it off once. So on this one, it ends up looking like dollars per unit, but not per unit squared, right? I took one of them off because per unit squared means per unit, it's there twice. So I just took one of them away. And then I will say when x units are produced. They almost look the same, right? When I'm writing down the language associated with it, you get a lot of it kind of for free. You just make a small change at the beginning where we remove one of, in this case, the pers, per unit.
So like if it would have said per unit cubed, it would be rewritten as per unit squared?
It would, yeah. And if it just said per unit, it wouldn't be rewritten at all, right? Like if this original equation said dollars per unit where x units are produced, then when I take the antiderivative, it'll just be dollars when x units are produced. The per unit would go away completely if it was only there once. Okay? All right, I want to talk, this is one more piece in this section, and it's actually finding a specific antiderivative. So you'll notice over here what we found was the general antiderivative. Did you guys see that? This one says specific antiderivative. What we're going to be doing in this problem is we're going to be doing just like we did before, but at the end, we're going to figure out what is c. We keep putting this random plus c on the end of everything, but it had an original value. We just don't have the tools to find the original value most of the time. But on this problem, we're given enough information, we can find the original value. So let me show you how we would do that. We'll start doing the exact same thing we'd done before. We take in antiderivative, so we're going to make a capital F of x. The 3.2 will stay because it's a constant multiplier. X to the 0.23 is a power rule. What will its antiderivative be?
X to the 2.3.
Plus one, right?
Plus 1.
Okay, plus 1 on the exponent, right? The exponent is currently 0.23. So what will my new exponent be? 1.23. Anything else?
Over,
Divided by 1.23. Precisely. What's the antiderivative of 4? Somebody's saying it over here. Good. 4x. Lovely. And then I need a plus c. Okay. So normally, that's where we'd stop because we wouldn't have this last piece right here. It doesn't exist. And we would stop the problem. We'd found the general antiderivative. We'd move on, right? Everybody good so far? That problem's not any different than the other ones we've done. It looks a little bit different because they gave it to us in an equation form with a name, as opposed to like the earlier ones where they just had the notation with that script S thing going on, right? But we actually have this last piece of information here as well. What this last piece of information tells us is that when x is equal to 2, my output of the entire function is going to be 7.8. In other words, when I replace x with 2, 3.2, 2 to the 1.23 over 1.23 plus 4 times 1.23 plus c, it will equal 7.8. That's what that notation at the end says. It says plug in 2 for x and your answer will be 7.8. So take a look then.
Plus like a 4.
What's that?
4 times 1.23. That was just 2.
Oh, it is. I'm sorry. I typoed it. You're right. There's a 2 there. I got carried away with my 1.23s. Yeah, 4 times 2. This equation that's all highlighted in yellow now, and hard to read, yeah, that one, only has one thing that's unknown, C. So I should be able to solve for it, right? Yeah. So grab your calculator, and you're going to let your calculator be able to find for you all of this, including the 2 that was plugged in correctly, like Paula found for me. So we're going to take and don't round things too soon. Keep everything till the end. We'll round it all eventually. 3.2 times 2 to the 1.23 divided by 1.23 plus 8. So I'm going to keep, I'll keep 5 decimals for now, just for safety's sake. 0.10256. I still have my plus c, and it still equals 7.8, right? That's what it is. What will I do to find c then? Close. It's not divide by. It'll be subtract. Yeah, we could end up in a place where we did division at this point, but this one's actually being added, so we will do the opposite and we will subtract. So we're going to subtract the 14.10256. And I will end up getting, with 3 decimals, because that's what we were using in class when we get to the end of the problem, negative 6.3 0, 3. Now, that's not the answer to the question, but I have all the pieces of the answer now that I solved for C. You okay, Ariel?
Yeah, you put it on the first one.
You're exactly right. Exactly right. Okay. You make it a little smaller so I have some space. So we're going to take the original, not original, but the equation that we found, which was 3.2 x to the 1.23 over 1.23 plus 4x. And we're going to plug C in, negative 6.303. And that would be my final answer for the problem then. That's the specific antiderivative. Now, notice, if you took the derivative of this, you'd get back where you started, right? The derivative of the 3.2x to the 1.33, the 1.23 would come down and cancel with the one on bottom. I'd decrease my power to 0.23, and I'd end up with that 3.2, and the 0.23 is an exponent. On this one, the derivative of 4x, that's 4. And the derivative of negative 6.303, that's 0. It would go away. I would end up right back where I started. So you should always be able to check and make sure that I've done it correctly. So here's the upside to antiderivatives, because somebody had asked me, do people usually do better on antiderivatives or derivatives? Because at that point, whoever it was a little discouraged with the derivative gateway process, I think. I said, usually antiderivatives. I said, and the reason is because we don't have any complicated rules. There's no product rule. There's no chain rule. We don't have any of that mess going on when we do antiderivatives. And the reason we don't is because while those things exist, it's actually a lot more complicated to do antiderivatives with them. And we're not going down that far into calculus. When our traditional calculus, like calculus for engineering and science majors and whatever does it, they encounter that in Calc 2. So that's the second course. So that's why that's not happening yet. So the antiderivatives tend to be more of the basic antiderivative form that you would have seen with basic derivatives at the beginning, and you liked that just fine. It was when it got complicated that it got harder, right? We don't have that component here. So take a look then with me with an application problem. We've seen this lab mouse before, different problems with him. The rate of change of the weight of a laboratory mouse can be modeled by the equation W of t equals 7.37 over t grams per week, where t is the age of the mouse in weeks beyond 2 weeks. In other words, if it was a 5-week-old mouse, t would be 3. It's how long it is after the 2 weeks. We've seen this before, if you remember. At an age of 9 weeks, which would mean t is 7, because that's 7 weeks beyond the 2 weeks, a mouse weighed 26 grams. Find the specific antiderivative describing the weight of the mouse. Okay, so this is the same problem we did here. The directions are. It just has context like it did here. So if we take our last two problems and we sort of merge them together, we get the context from one piece and we get that whole specific antiderivative language from the other piece, we end up with my lab mouse problem. Okay? So we're going to take this equation and we're going to find the general antiderivative. So first of all, it's going to be a capital W of t. What's going to happen with the 7.37? It's just going to come along for the ride, right? It is. So we've got 7.37. What's left is the 1 over t part, right? If I pull the 7.37 out in front, I have 1 over t. So what's the antiderivative of 1 over t? You've seen it happen a couple times. Who said it? You're right, Savon. Good job. So it's ln of t. And we are going to go ahead and be a little careful that it's absolute value of t because it says weeks beyond 2 weeks. And technically we could talk about like what happened on week 1. And that could be problematic in terms of the way that the structure of the language is here. So let's put the absolute values on just to be careful. What else do I need? Plus c. Right. Now, the piece of information right here is the other piece of information given to me in that last problem. That's telling me that W of a specific value equals my 26 grams. Now, typically it would just be W of 9, but they aren't measuring the weeks like that. It's actually 9-week-old mouse, which means he's 7 weeks beyond the 2-week mark, so it would be 7 here. So W of 7 is equal to 26. So if I use that information down here then, I can put the 7 in for T. So 7.37 natural log of 7 plus C, and it should equal 26 grams. And we'll solve. So 7.37 natural log of 7 is 14.3414 or 34136, I guess. It doesn't matter. We're going to round it off at 3 decimals here in a minute anyway, but we'll just keep a few extra for the moment. Equals 26. And then we'll subtract that from 26, right? So I have 11.659. So if I stop here, am I good? Oh, I'm not good. I mean, I'm not bad. I've done a lot of the work, but I'm still missing pieces, right? So I need to have this whole equation in its complete form. So it was W of T equals 7.37 natural log of X, or T, sorry. T is my variable. Plus 11.659. That's the equation part of it. But I need to have units. So let's go back and look at how the units were described originally. Originally, my units were described grams. Well, let's just do part of it at a time. Let's do the grams per week part. Grams per week, that's my output units. So I'm taking the antiderivative. So using that information, what's the output going to be on my antiderivative? What do we do over here? We took off one of the per units, so it no longer said per unit squared, right? So we took off one of the per parts, but here there's only one of them, per week, right? So it'll just be grams. It's exactly right. Output is just plain old grams. This is actually measuring how much the mouse actually weighs. That's what it does. Okay, the first equation it gave us was how the weight's changing. This one's telling us what the weight actually is. It's the number of grams of this mouse. The other part then will simply mimic what's already there. It says where T is the age of the mouse in weeks beyond 2 weeks. We get it for free. We could write it down exactly like it already is. Where T is the age of the mouse in weeks beyond 2 weeks. Okay? So, what I want you to see is this. Do you see the homework listed at the bottom of this page? Y'all see it, right? Do you know why there's so many? There's 2 reasons. Any guesses? I'm sorry, I can't hear you, Paul. No. Okay, number 1, there's 2 sections of material. I get that, so that's not really the answer to my question. But there's a section 5.4 and there's a section 5.5. Most of these will be fast. Because most of these problems are gonna look like A, B, and C at the very beginning, okay? Almost all of them. Almost all of them are gonna be like A, B, and C. They're gonna be quick, right? It's like giving, the first grader a whole bunch of addition problems. They're gonna work through them very quickly because there's just not a lot to do. You don't have to simplify a whole lot. You don't have to write any language down. So it's gonna feel like there's a lot of problems, but they're gonna feel like they move through very quickly, okay? Also, I want to make sure that as you're doing these problems for Thursday, that you are getting really good at doing these antiderivatives, because that's what that quiz is on Thursday. It's the last opportunity that I have for you, at least in my plan right now, for any kind of extra credit. I'd love for you guys to be able to pass that quiz on the very first time and get those bonus points. That would be fantastic, wouldn't it? Yeah, it would be great. So the more you practice on the problems that are like those, the better your chances are of being able to pass that quiz on the very first time. Not to mention that it means you won't have to come find me in my office and all that stuff and take more time up to do so, right? Because it takes up your time to do that. So what I'd like for you to do right now is to get out this list of problems if you don't already have these out, or pull it up on your phone if you're pulling them up from there. This is what I want you to work on. You don't necessarily have to go in order today if you don't want to in class. Please put them in order for the grader so she's not like struggling to figure out where you put problem number 7 or whatever. But if you want to like skip a space and bounce around a little bit, you could do that. I'll be filtering around as you work so that I can answer questions, hopefully, as you encounter things that might feel like they're somewhat different than something that I did, so that we can make sure that everybody's on track to be able to do very well on that quiz on Thursday, okay? So there's a list of problems here. They're inside of Canvas. If you don't want to pull Canvas up, you can like take a picture of my paper. That's fine too.